Hello everyone, welcome to Practical Mechanics. I'm Mohsen. Today's video is about how to draw bending moment diagram. From the previous video that we learned how to draw shear force diagram, I keep that example and wanted to draw its moment diagram, bending moment diagram as well. Let's look at the previous example. We had a simply supported beam with 20 feet is length, span, and 300 pound per foot uniform distributed load that is applied to the beam. And then first we consider the free body diagram. We separated the beam from its supports and find out reactions at the support. And we found that Ay is 3000 and By is also 3000 pound. Then we solve the equations of equilibrium to find out the reactions at the supports. And then for drawing the shear force diagram, we just consider again the same beam under subjected to uniform distributed load. And then we consider a portion of the beam because the loading conditions, as I said in the previous video, that the loading condition doesn't change from the first to the end. One cut is enough. And when you make the beam into pieces, you have to consider left portion or right side portion. And then we consider the left side portion and we show at the cut sections shear force diagram in the direction that is actually assumed and bending moment. We calculate the V shear force and we draw it from 0 to 20 feet for the beam. Then here we wanted to calculate M, bending moment, internal bending moment inside the beam, and draw it with respect to from 0 to 20. Okay. When we take summation of moment at C, the cut sections equal to 0, we reach to this agreement equations that 3000 times x distance produces a moment here in clockwise direction. We assume our conversion is negative. 300 times x, the length of this portion, 300 pound per foot. 300 times x is the equivalent concentric forces, 300, and it produces about this point, it produces counterclockwise moment, which is considered positive, 300x times distance. Distance, if the portion is x, this distance is a half x. X over 2. Then times x over 2. And we don't have anything else except m. We add m counterclockwise positive equals 0. Then let's simplify that, keep m at the left, and move everything transfers to the right side, and simplify that. It is minus 150x squared plus 3000x. That's the bending moment equations between 20 feet and 0. Actually, we wanted to draw this curve. This is similar to a curve. M is a function of x is equal to ax2 plus bx. You remember it from algebra. We wanted to draw this curve here from 0 to 20. Okay, let's draw x-axis and vertical axis m. Pound foot is the unit. And if x is equal to 0, the value is 0. Then at x equal to 0, m at 0 is 0. At x equals to 20 foot, m at 20 also is 0. This is 20 over 2 is 400 times this one minus 60,000. 20 times is 60,000 minus 60,000 plus 60,000, 0. Then we need more point. At the middle, because this is a 0 here. Here is 10 foot. Here is 5 foot. Here is 15 foot. Let's draw. At 10, if you substitute x is equal to 10, 100, this is minus 50,000. 3,000 times 10, 30,000. Minus 50,000 is 50,000. Okay. Draw it. 15,000 here. At 10, we have 3 points, but because it is a curve parabola, we cannot draw it by 3 points. I need more points. For example, at 5 or 15, I substitute 5. If I substitute 5 here, 25 times 150 plus 3,000 times 5, 15,000 minus 3,750 is equal to 11,250. Okay, close to that. If it divided into 3 pieces, 5,000, 10,000, 15,000, this is 11,000 at here, approximately. If you use 15 as well here, 225 times this one, 30,000 times 15, then you reach to the same value, 11,250 is here. You can reach this value here. And then when you connect these 3 points, you reach the equations of the bending moment. And the maximum is at the middle, the max, which is 15,000 pound-foot. Then, for calculating the bending stress in beams, we always are looking for worst case scenario, which is maximum bending stress. And maximum bending stress happens when M is max and when distance of the point from the cross section is max. Assume an I-beam. This is neutral axis. Again, that point is the maximum distance, the upper flange or lower flange from the neutral axis. Again, bending maximum stress, maximum bending stress is equal to when the M is max and when distance from the axis is max, Y max divided by moment of inertia. Then, for M max, we need to draw bending moment diagram. All the beams are not so simple. I started from the simplest case. There's a uniform distributed load. And you see the maximum moment here is 15,000. But for some beams, this is complicated, that we will see in the other next videos, that we added some loads, concentric load to this one, or a portion is under uniform distributed load and the other portions is under concentric load, and also point bending moment, actually. And then you will see that the bending diagram, moment diagram, is a little complicated. We have to draw it until to find out what is the maximum bending moment, internal bending moment that happens inside this beam, in order to substitute in this formula here to find the maximum bending stress in beam. Okay, thanks for your watching. See you in the next video.